Hi, stat students. Welcome to section 4.2. So we're talking about probability. Remember, chapter 4 is all about probability, which is the basis for inferential statistics. So we're going to talk about addition rules. This is a very instinctive thing. You've already done this. You know this. We're just putting it into more formal terms. So please don't overthink this because you know this. So first of all, we're going to do Venn diagrams, which are actually a really interesting and different way to create a visual representation for finding probability of compound events. So compound, remember, is more than one thing happening. So let's say that we want to select a senior at Marine City High who's taking statistics. So this whole box that I put into your notes is all of our Marine City High School students, 100% of the students. Well, 100% of the students are not taking stats and 100% are not taking or are not seniors, right? So I'm going to create a little bubble right here. This bubble is all of our seniors. Now, if I'm going to make another little bubble for the people who are taking stats, let me make it over here. So stats has to be Marine City High, right? So that's going into that Venn diagram. Is it standalone? Are seniors also in stats? Are stat students also seniors, right? So they have to, but all seniors are not stat students. All stat students are not seniors. So I've got an overlap. So I've got some seniors who are taking stats and some stat students who are seniors. I could put different bubbles if I asked a different question, but I've got an overlap. They are not the same thing. They do have an overlap. So Venn diagram to represent that. So let's talk about mutually exclusive events. So mutually exclusive events are events that cannot occur at the same time. It just can't happen. You can't be a freshman and a senior at Marine City High. Those are mutually exclusive. They can't occur at the same time. So they have no outcomes in common. And they also are known as, in the book, they call them disjoint or disjointed events. I stick with mutually exclusive, but if you run across that term, you'll know why. So if we're going back to our basic, our example probability stuff that we always use, we could say that rolling a die and getting both a 4 and a 6 are mutually exclusive events because they cannot happen at the same time. So I'm going to start out by asking you, are these events mutually exclusive? So example B, it says we roll 2 dice. Event A, the roll has a sum of 7. And event B, we roll doubles. So can we get a sum of 7 and roll doubles at the same time? We can't, right? That can't both happen. So these are mutually exclusive. They cannot happen at the same time. Since we're talking about elections lately, example B says if we're going to select one registered voter, one person, we're going to just draw a name. Event A is they are a registered independent voter. So they're not a Democrat or a Republican. Event B, the voter is a registered Republican. Well, you can't be both an independent and a Republican at the same time. Those are mutually exclusive events. Sometimes that's not a good example because people don't know about registering within a party, so maybe not the greatest example. C. So I'm going to draw one card out of our deck of cards. We've got that sample space in section 4.1. Event A, selecting a face card, and event B is selecting a heart. Can that happen at the same time? Could I have a face card that is a heart? That could happen, right? So these guys are not mutually exclusive. They can happen at the same time. We already did example E. Example E says selecting a freshman at Marine City High who is a statistics student. Well, you might have to know that I don't have any freshmen or sophomores in statistics, so that cannot happen at the same time. So these are mutually exclusive. These guys are not mutually exclusive because it could happen that you have a senior who is also a statistics student. So just kind of working through that terminology. So now let's talk about the actual title of the section, which is the addition rule. The addition rule goes for mutually exclusive events. Notice my Venn diagram. So this whole box right here, the probability is equal to 1. So that's one whole thing. Probability of A is this bubble over here. The probability of B is this bubble over here. Notice how there's no overlap, right? So they cannot happen at the same time. So when you've got mutually exclusive events, the probability of A or B happening, we add the two probabilities together. I don't know if you want to write down the second bullet. Perhaps you recognize the math symbology from this, but the probability of A in union with B, this little guy means union. Not sure if you've seen that in your math classes. That means you add your two probabilities together. Don't overthink this. You're going to add at some point. You might add in the beginning or you might add at the end, but you are going to add, and it couldn't hurt to write down or means to add. So practice 10 says, if we're going to find a probability at a convention, there are 7 math instructors, 5 computer science instructors, 3 statistics instructors, and 4 science instructors. This is a very techie convention. None of the instructors teach in more than one discipline, so a stats teacher cannot teach computer science in this particular case. If one instructor is selected, find the probability of selecting a science instructor or a stats instructor. So the probability of science, whoops, can't spell, science or stats, right? That's really what it's asking if we're going to put that into our stats symbols. So remember, probability is equal to favorable over possible. We can do this one of two ways. We can figure out how many science instructors and how many stats and add them, or probably your first instinct is just to add at the beginning. So let me make sure I address that before we move to the next slide. So how many instructors are there altogether? It looks like, is there 19 instructors? That seems like a weird number. I'm going to break this down just so you can see it. This is my science. This is my stats. And science instructors, I've got 5. Stats instructors, I've got 3. So this is going to be 8 out of 19 is the probability. We could go to a decimal if we wanted. We don't need to. Am I right on my science instructors? I'm wrong, right? Oh, gosh, I was looking at computer science. Let's make that 4. Sorry if I confused you. That should be 4. I was looking at computer science. I just saw the word science. Anyway, so you might have just said to yourself, well, over here, if it's asking for science or stats, there's 7 possible teachers who are in one of those disciplines out of 19. You add it at the beginning or you add it at the end. The only reason I'm showing you this way is because later the problems get a little bit more technical, so I want you to understand what we're doing. But if you just did 4 plus 3 is 7 out of 19, you are right, and mark it right, and you're good. All right, so the probability of 2 events that are not mutually exclusive. So notice in our Venn diagram, I've got 100% is here, whatever that is. The whole box has to add up to 1. And notice my probability of A, whoops, is this bubble. And then I've got that overlap probability of B. So I've got a whole big bubble that is the probability of the first event, a whole big bubble that is probability of the second event, but they go together, they overlap. So this formula, the probability of A or B is equal to the probability of A happening plus the probability of B happening. So this left-hand bubble over here plus this right-hand bubble over here. But then we have to take out this overlap, the and part, the part that has both bubbles involved. So why is that intersection subtracted? Because we've already counted those people or those things in probability of A, and then we count them a second time in the probability of B. So we subtract that because it would be double counted. It would be counted within each bubble. Probability of A and B would be double counted. I'll put one for each bubble. Once for each bubble. Sounds better. I'm pretty sure bubble is the technical term in a Venn diagram. So then I got technical with the symbols of it. So the probability of A union B, so A and B, sorry, A or B, remember, is the probability of A plus the probability of B minus this guy right here means intersection. So that double counted, intersection actually stands for and. Union stands for or. And I do want to mention that we could have more than two bubbles. Oh, I thought I had something else there. So when A and B are mutually exclusive, if the bubbles don't overlap, then the overlap is 0. So if you're not sure, treat them as not mutually exclusive, because if you subtract 0, then it's really not a big deal. It doesn't change anything. But remember, this is not mutually exclusive. So they do overlap. They can happen at the same time. Going back to that example, maybe bubble A is drawing a heart, and maybe bubble B is drawing a face card, right? There is an overlap. It could happen. Both things could happen, or it might not. All right, so if I'm going to give you a table, data in a table, there's a study involving 300 patients. This is a very uplifting example. Of the 100 alcoholic patients, 87 of them had high cholesterol. Of the 200 non-alcoholic patients, 43 had elevated cholesterol. And we've got this large table. So notice we've got totals going on in the bottom column and the right-hand row. So watch for those. The data, it broken down, really is within this 4 squares. So find the probability of an alcoholic with elevated cholesterol. So we're looking for alcohol and elevated cholesterol. Well, it looks like that's going to be 87 favorable over the possible, wasn't it 300 possible patients. We could turn that into a decimal. I think it's like 0.29 or 29% or something like that. Probability of a non-alcoholic. So how many patients were not alcoholic? Right here, 200 out of 300. So that's going to be like 67%. Notice letter C. I want to make sure I mention this one. An alcoholic or elevated cholesterol. So alcoholics are 100 out of the 300 plus elevated cholesterol would be what? Elevated cholesterol. There's 130 with elevated cholesterol if I'm going to the totals. But please notice, maybe I'm overthinking this, but I've got 87 that fall into both of those categories. So that's that intersection. I have to take that out. You might read the table a different way and still end up with, what is that, 143, I think, out of 300. If you read the table differently, no worries. But the or tells us we have to add. They can happen at the same time, so we have to subtract in some way the overlap, the A and B. All right. Sometimes they give us a table like that, a lot of information, and you have to kind of work through it. Let's do this one. Let's make ourselves a Venn diagram. So pizza. Everybody likes pizza. Well, I hope everybody likes pizza. The probability that a customer selects a pizza with mushrooms, M, or pepperoni, P, let's simplify things, is 0.5. Mushrooms or pepperoni. The probability that a customer selects only mushrooms is 0.32. If the probability that he or she selects only pepperoni is 17%, find the probability of the customer selecting both. It's a lot of words, right? So let's make ourselves a Venn diagram. So this is all pizza land right here. Within that pizza, we could select mushrooms. We could select pepperoni. But you could select both. So we do have an overlap in there because you could have mushrooms and pepperoni on your pizza. So let's label this stuff up. So it says only mushrooms is 0.32. So mushrooms only is 0.32. So this whole big bubble over here is 0.32. That includes the overlap. Mushrooms or pepperoni is 0.55. So the whole, all the bubbles together equals 0.55. I need to put that on the back burner for just a second. Actually, we could ask this question now. If somewhere within these two bubbles is 0.55, what is the probability that they get some topping other than mushrooms and pepperoni? Well, 0.55 is inside the bubble, so 1 minus that 0.55. So some other topping is going to be 0.45. I need to see that calculation out there. 0.45 is floating with something other than that. Let's see. Only pepperoni is 0.17, so my whole big pepperoni bubble is 0.17. So I need to figure out how much goes into the overlap. So I have 0.55 to work with, right? So only mushrooms is 0.32. Only mushrooms, I say that wrong before, only mushrooms does not include the overlap. Only pepperoni does not include the overlap. So I'm wondering what that is. So 0.32 plus the 0.17 is a 0.49. But 55% of customers get mushrooms and or pepperoni. So what is left to go in this little overlap right here? If my math is right, I think that's going to be a 0.06. If I add up 0.32, 0.06, 0.17, and 0.45, I should get 100% or 1 for all of ordering pizza. All right, do you want to do this last one, or maybe I should have you do this last one, create a Venn diagram. The probability of A is 0.36. The probability of B is 0.42. And the probability of A and B, so this is the overlap, is 0.16. So I need to figure out how much goes into the rest of bubble A only, how much goes in the rest of bubble B only, and how much is out here for the rest of the probability so that it all adds up to 1. So fill that in. Let's see how you do. And that is the end of 4.2. So we're going to do a lot of adding with probabilities. Remember, you're going to add at the beginning or add at the end, but somewhere you're going to add. So don't overthink this. This is instinctive. Thanks for sticking in there for section 4.2. See you next time.